Hi guys, welcome to the fourth tutorial of our embedded systems course. We will take a look at a new concept for our Arduino board. We will start with this example, which will lead us to our new concept. Okay, this example says that an AVR, which is our board, lets us turn outputs on and off, meaning that we can send either 0 volts or 5 volts. Okay, but what if we wanted to control the brightness of an LED, meaning that we wanted the LED to be have medium brightness or very, very dim, or we wanted to control the speed of a motor, whether it's very fast, intermediate speed, or having a very slow speed. To do so, we need to send changing or alternating voltages. We cannot control the speed of a motor with just 0 and 5 volts. We cannot control the brightness of an LED by 0 and 5 volts. So we need to change the voltage value which is sent to our components. But unfortunately, cannot happen in our board. We cannot change the values which is sent to the components. We cannot say that we want to send 2.5 volts, and the next step we wanted to send 1.5 and 4.23. We cannot do that, but we will have an alternative approach to change the voltage of our board. The voltage of the board is constant, which is 5 volts. We want to alter it. Okay. How? We have an approach saying that we can take the voltage source, connect it for a second, and disconnect it for a second. Okay, this means that it is on, it's 5 for 1 second and 0 for 1 second. This period, or this time which is on, it's 2 seconds. 1 second of the 2 is on, it's 5, and the second second is 0 volts. So stepping it up, if we manage to speed this up so that we disconnect the power supply over 1,000 times a second, we can fool the power supply into thinking that our signal is half the value of the power supply. Okay, what does this mean? This means that we want to keep on, turning off, turning on, turning off over the whole period of time, which is the board sending the voltage source, the voltage value to the component, to have an average voltage of 2.5 instead of 5. Let's say that our LED will be will have medium brightness at 2.5, which is actually yes, because the maximum voltage is 5 volts and the medium or the half of the volts is 2.5. So we want to send 2.5 volts to the LED, not 5. Our alternative way is to keep on turning on and off our power source across the period to have an average voltage of 2.5. Okay, what this is called? This is called something called pulse width modulation. Pulse width modulation is a technique for getting analog results with digital means. Digital control is used to create a square wave, a signal switched between on and off. This is on-off pattern can simulate voltages in between full 5 volt and 0 volts, which is off, by changing the portion of the time the signal spends on versus the time the signal is spent off. The duration of on time is called pulse width. To get varying analog values, you change, adjust, or modulate that pulse width. To work with the PWM, we need to understand two of its basic definitions to be able to use it well. The first thing that previously we said that we can turn on the turn on the signal for 1 second and turn it off for another second, turn it on for 1 second and turn it off for another second. If we have, look at this figure, if we have a period of 500 milliseconds, okay, and we have the on signal or the width is on for 250 milliseconds and off for 250 milliseconds. The duty cycle is called 50%. The duty cycle is the percentage at which the signal is on per one period. Okay, as we can see here in this figure, we have a period of 500 milliseconds, and the width, which is on of the signal, is on for 250 milliseconds and off for 200 milliseconds. So over one period of time, T is the period, over one period of time, we have 50% on and 50% off. So the first definition is the duty cycle. How long is the signal is on versus off? Okay? Okay. The second definition is the frequency. The frequency is the number of times a particular event repeats itself within 1 second period of time. Okay, it has a period, it has a unit of hertz or cycles per second. Okay, we will take the hertz unit. Okay, here we have our period is 500 milliseconds, but here in the definition we are talking about 1 second. Okay, 500 milliseconds, which is half a second. So we need to know the frequency of this particular signal. Okay, so multiplying our we will not gonna multiply, we will just duplicate this again. We will have on and then off again. Okay, over one second period of time. So we have the signal is on twice for 50 seconds over 1 second period of time. Again, we are trying to understand the concept of the frequency. The frequency here represents the speed at which the duty cycles happen. Okay? Okay, the frequency is measured over 1 second of period. Okay, but here in our example, we have the example over half a second. So if we duplicate this signal, okay, so on and then off, we will have over 1 second, because this is over half a second, we will have the on twice and the off twice. Okay, this is 2 hertz, that our event repeats itself twice over a 1 second period of time. Okay, so now we need to understand 2 concepts again to be able to work with the with the PWM, the pulse width modulation. Okay, the pulse width modulation is an approach to have an analog output in digital means, meaning that we are trying to alternate the voltage output through turning on and off the signal with a particular percentage, okay, over one period of time. Okay, to have an average voltage which we want. Okay, because we want to have values between 0 and 5, but our board only outputs 0 volts and 5 volts only. We cannot have intermediate values. That's why we are using the PWM. Okay, so the first thing to do is to identify the duty cycle, which is the percentage at which the signal is on per one period. Okay, Okay, the second step, which is the frequency. The frequency is the number of times a particular event repeats itself within 1 second period. As we said that this is a 500 milliseconds period, which is half a second. Okay, when we replicate this again, here up and then down, we will, over 1 second, we will see that our on signal is on for twice per 1 second. The frequency here corresponds to the speed. Okay, imagine with me a motor. We want to increase its speed. We will work with the frequency rather than the duty cycle. The duty cycle already is settled. Okay, we need to work with the frequency. Okay, let's have a look at this this question. It says, when you take a square wave, it is on for a while and off for a while. If we divide the on by the period and multiply it by 100, we will get what is called a duty cycle. Okay, so the question is, write down the duty cycle expression in terms of on time and off time. Okay, as we discussed earlier, that the duty cycle is the on-off versus the on plus the off time multiplied by 100 to get it in percentage form. So our expression for the duty cycle is the on time divided by the total time of our signal or our period, as we discussed earlier. Here, that our total time was 500 milliseconds. We were on for 250 milliseconds, which was half of the total period that we have, which is t. Okay, so as we can say, we can get back here, the on time was 250, the on time 250 plus off time 250 times times 100, we will have a 50% duty cycle. Okay. Okay, the second question, it says, assume we are on for 1 millisecond and then off for 1 millisecond. What is our duty cycle? Let's find out. Our on time is 1, off time is 1. The duty cycle is the on time, over the total time, which is on plus an off, times 100 to get it in percentage. Okay, so in this question we have the duty cycle of 50%. Okay, assume that we are on for 1 millisecond and off for 3 milliseconds. What is our duty cycle? When we see this, the on time is 1 millisecond, off time is 3 milliseconds, so 1 over the total, which is 4, times 100 is 25 milliseconds. 25%. 25%. Sorry. Okay, so now we want to have the actual voltage value after we altered or modified our pulse width. So here it's saying define the PWM output voltage in terms of duty cycle and input voltage. Okay, our input voltage is always the V, the 5 volts, okay, which is the default value of the Arduino board, which is 5 volts. Okay, the duty cycle is what we got previously in this question and in that question. Okay, so now we can actually know the altered value when we multiply the duty cycle to the input voltage. Okay, now it is saying, the question is saying, we want to command an analog actuator, which is some sort of a motor with a 1.25 volts signal. What should we do? Explain the reasoning. Okay, so now we want 1.25 out of the 5 volts. Okay, so as this previously says, we know the output voltage, we know the input voltage, we need to get the duty cycle, right? So in the Atmega, as I said before, we have a 5 volts power supply. So we will connect the actuator to one of the PWM pins, activate the PWM on with 25% duty cycle. Why 25%? If we go back to our definition of the output voltage after the pulse width modulation and the input voltage, which is 5, we have the relation between them is the duty cycle, okay? And here we have the expected output, which is 1.25, and we know that we have a 5 volts in the Atmega, so we will just substitute this equation. Here we will write input voltage, we will write the 5, and here you will type 1.25, and then divided by 5 we will have 0.25, which is the duty cycle. Question 1, part B. Much like the counter functions, PWM can be simulated in software. However, the hardware version is preferred. With very little coding, you can get a constant square wave going. It uses internal timers. The question here says, the PWM could run at different frequencies. Why is this important? Explain it with real-life examples. Why we need different frequencies? Why do we need this? Can we just have one frequency across all the applications? No, we cannot have this. Why? Because very fast frequency, it may lead to overheating, and actually the components would break down, and having very, very slow frequency could result in lagging. We can read the answer here. We can say that this is important, or having different frequencies is important, because some devices are sensitive to the PWM speeds. A motor, for example, will get hot if the PWM waveform is too fast. It is changing from 0 to 1, 0 to 1, 0 to 1, very, very fast. It might burn it, or it will jitter, having lags, if the PWM is too slow, like having 0.025 hertz per 1 second. This is very, very, very slow. The motor would lag, and it would not function the way that we wanted it to function. That's why we need to take care of setting the frequencies according to each and every component, to have the perfect output, which will make our component work as perfectly as we want. Question number 1, number C. How many PWM outputs does the Atmega 328P have? Refer to the datasheet. Where they are located? What do you notice? Okay, now we will go to the datasheet and extract the information, as we don't memorize it, and we won't memorize it because we are learning a concept of understanding the PWM. This concept is present in all the microcontrollers and all the boards that we might tackle in the future, so it's going to be easy to know how to read the data sheet and how to extract data from it. That's why we will be using it to extract the number of PWM channels and where they are located on the board. Now we are going to work with the Atmega datasheet as shown here. Okay, this is a very long one. You will not be giving this in the exam, but you will be giving the parts that you will be needed in the questions where you have to extract data from the data sheet. First of all, we want to extract the number of pins which support the PWM function. We will use the data sheet for our Atmega 32P, which is the UNO board. As we said before, that we will work with the UNO board, and whatever it has, it is duplicated in the Mega board, which is the bigger one, to extract such information. First of all, we need to know how many pins and their location. We will just search for it, like Control F, the PWM, and see how the result will be. The first result is the number of bits of the PWM. It shows here in the very first page that it has 6 PWM channels. Okay, now this is the first part of the question. The second part is where they are located, at which ports, and which pin numbers they are in the board. We will just literally just click next. Okay, nothing here. We will start with port B, bit number 3. It has the PWM mode timer function. That's the first pin. We will have next port B, bit 2. The third pin is port B, bit 1. The fourth bit is port D, bit 6. The fifth pin is port D, bit 5. And the sixth bit is port D, bit 3. Okay? After extracting the data from the datasheet, we can say, or we can conclude, that we have 6 PWM channels on the Atmega 328P. These 6 pins are located, 3 of them on port B, bit 1, bit 2, bit 3, and the other 3 on port D, bits 5, bit 6, and bit 3. Each 2 of these bits are located on each timer / counter. We will talk about this while solving the next questions, that the PWM works using internal timers. Before jumping to the next question, we need to remember what we have mentioned earlier about the PWM, that it has 2 parameters, which are the duty cycle and the frequency. The duty cycle is the percentage of one period a signal is on, and the frequency is the number of times a particular event is repeated within this 1 second period. The duty cycle here is about the wave, which is in our case is the maximum value of the Arduino could possibly generate, which is the 5 volts, and we are trying here to over one period of time, having an average of this voltage to have a different output at the end. Here in this example, instead of having per one period 5 volts, we will have 2.5 volts, because this wave is on for half of the time versus off the half of the time. Okay, so in the next question we will talk about how the Arduino has options where it can generate this on wave with different modes, not just one mode, and you'll understand that next slide. Next question says, refer to the datasheet. The AVR's PWM timer is capable of running in different modes. What are they? Going to the datasheet, we will find that the PWM timer has multiple modes of generating the signal wave. Okay, we have the first mode, which is the fast PWM mode. What does this mean? This means that this is the figure on which the fast PWM mode works. This is the timing diagram. Means that the counter starts from 0 until it reaches the maximum or the top value, which is FF or 5 volts per period, as we said, but in the next period, the timer clears to 0 and then starts incrementing till it reaches the top, and then what it does, it just clears and then increments, clear, increment per period to generate our waveform. Okay, imagine with me the LED. When you turn it on, turn it off, turn it on and turn it off without actually dimming it, without like reaching the let's say the maximum brightness, and then trying to decrement the brightness until it is fully dim. In this mode, the counter only incrementing on the way up until it reaches the maximum value, then it clears to start in the second period from 0 till it reaches, etc. This is the first mode, which is the fast PWM mode in the wave generation. Okay, when we go and check the other one is the phase correct PWM mode. As you can see here, the timing diagram is a bit different. Why? Because the counter starts from 0 like the previous one. It increments its counter until it reaches the top value. Okay, the fast mode does the same thing, but here it does not clear. It decrements its value until it reaches 0 and then increments its value until it reaches the top value. Decrement, increment, decrement, increment. It's like increasing the brightness of the LED until we reach the top or the maximum brightness, and then on our way down we decrease until we reach the 0 or the fully dim value. So we can say that we have two modes for the PWM. We have the phase correct mode and we have the fast PWM mode. Next question. Also, we are going to refer to the datasheet to look up the registers which are concerned with setting the PWM modes. We have seen earlier that we have two modes, the fast PWM mode and the phase correct PWM mode for the waveform generating. So we need to check the registers responsible for these modes. Going back to the datasheet to extract the registers responsible for generating the PWM modes, we said earlier that we have 6 PWM channels. These 6 PWM channels, each 2 of them are on 2 timer counter controlled registers. We have timer counter control register A and timer counter control register B. Okay, we have TCCR 0A, TCCR 0B, TCCR 1A, TCCR 1B, TCCR 2A, TCCR 2B. We have 6 timer counter control registers. Okay, each two PWM channels lies on 2 of these counter control registers. Okay, so we want to extract the bits which are responsible for generating or selecting the modes. Okay, here in the in register A, in the least 2 bits, we will see WGM 20, WGM 21. These 2 pins, we can scroll down to see their description. Bits 0 and 1. These bits are the waveform generation mode. okay, combined together and combined with one bit in register B, which is WGM22. We can select whatever mode we want, okay. We can see here the table, okay, with our three bits which are responsible for generating, or sorry, for selecting the waveform generation mode. We can see here the PWM phase correct, okay. When we select on the two registers together, WGM2, WGM1, WGM0, when we select 0, 0, and 1, we will have the phase correct PWM mode. When we select 0, 1, 1, we will have the fast PWM mode. When we select 1, 0, 1, PWM phase correct, but with a change of the top value, as we have seen in the timing diagram, that the counter keeps counting until it reaches a top value. The top value can be FF, meaning it's the maximum value, right? Which is 5 volts. FF, like four ones and 4 ones. Here in this OCRA, it's a value which can be put or selected by the user. Okay, so we can put our maximum value here to indicate the maximum count that the counter can reach. Okay, instead of having the 4 ones, we can have like half of the top value, okay, and so on and so forth. Okay, so again we have two registers, okay. They are responsible for selecting the waveform, wave generation form. We have two registers together, the timer counter control register A and timer counter control register B. In this register, in register A, we have the least 2 bits, WGM0 and WGM1, and in register B, timer counter control register B, we have only 1 bit. The combination of the 3 bits lets us select whatever mode we want, whether it's the phase correct or the fast PWM. And on top of selecting the mode, we can actually again select our top value at which the counter can reach per period, okay, whether it's the maximum value or a value which we can specify. Next question. I'm interested in the fast PWM mode. How do we select this mode? We will go back to the data sheet and we will get back to the table, okay. We have to choose the combinations of the WGM2, WGM1, and WGM0. These bits are in TCCR A, and this is in TCCR B, or timer counter control register. Okay. Okay, so since we want to choose the fast PWM, we will choose either this combination that WGM2 is 0, WGM1 is 1, WGM0 is 0, or we will choose this, WGM is 1, WGM2 is 1, WGM1 is 1, and WGM0 is 1 for us to choose the fast PWM mode here. Next section, due to the high frequency of the PWM mode, it is best used for DAC, analog to digital converter, fading LEDs, and power regulations. Explain how does the fast PWM work. Extracting the timing diagram for the datasheet, as we have seen it earlier, we have a counter and a compare bit. The counter starts from 0 up until the top value, whether it's the predefined top value, which is 4 zeros, which is 15, or the value which we can select. We can have whatever top value as wished. Okay, so this bit checks the value of the TCNT until it reaches the top value. When it reaches the top value, the OSN, we can say it triggers the counter to start again from 0. In the next period, it starts from 0, increments until the top value. When it reaches, when the counter reaches the top value, this triggers the compare bit to overflow the TCNT counter to start again from 0, and so on, so forth, so on, so forth. Last question is about the equation used to calculate the frequency of the fast PWM mode. The frequency is as follows: is the clock speed divided by the prescaler value multiplied by 1 plus the top value. The clock speed and the prescaler values. For more information about them, please read their explanations of how to get them from the datasheet. Okay? Thank you so much for listening to this tutorial for the pulse width modulation.